Hello, my name is Sevgi Gurbuz. I'm an assistant professor in the University of Alabama at Tuscaloosa. I'd like to thank everyone for coming to my talk today, which will be entitled Cross-Frequency Training with Adversarial Learning for Radar Micro-Doppler Signature Classification. This is work that I did together with my graduate students who are also listed on this paper, Mahbub, Emre, and Trevor, as well as a colleague of mine in the Technical University of Delft, Dr. Fiorinelli. The motivation for this work is to try to improve the ability of us to classify micro-Doppler signatures using deep learning. Micro-Doppler signature classification has a number of applications, including border control and security, perimeter surveillance, applications to assisted living, remote health monitoring, the detection of gait abnormalities, as well as falls, as well as, more recently, the use for RF sensors in human-computer interfaces for the purposes of gesture recognition. In all of these above applications, which utilize micro-Doppler signature classification, a key challenge is how we actually train the deep neural networks when we don't really have a large amount of real RF data available. The acquisition of RF data, especially for the purposes of human motion studies, is both time-consuming as well as potentially costly. There are a number of methods available to us for trying to deal with the problem of classification when we have low sample support. One of the principal methods that has been developed over the years is a technique called unsupervised pre-training. In unsupervised pre-training, we take advantage of the symmetric encoder and decoder structure of autoencoders to basically force the network to learn an identity mapping between the inputs and the output. An additional kind of innovation on this topology is the convolutional autoencoder, where convolutional layers are added to the encoder and decoder structure. And this allows us to be able to take better advantage of local spatial variations through the convolutional filtering. And this technique has been shown in prior works to generate some very good results on micro-Doppler signatures, even when we have a low amount of samples. Alternatively, another method that we can use for dealing with the small amount of training data available is to use transfer learning from data in a different domain. One commonly used domain in radar signal processing is actually the ImageNet database. And by using optical imagery, we can pre-train the weights on a DNN in the optical domain and fine-tune with a small amount of real data in the RF domain before finally using the fine-tuned network to classify and test on real RF data. In prior work, we've done a comparison of the performance of such techniques on micro-Doppler signatures. And what our work has shown is that if you exceed a certain minimum threshold in terms of the number of training samples, that the convolutional autoencoder does perform better than transfer learning. So if you look at the plot on this slide and focus on the red curve, which is the results obtained from VGGNet, and compare this with the blue curve, which is the results obtained using a convolutional autoencoder, you can see that once the amount of training samples surpasses about 650 samples for this particular classification problem, that the convolutional autoencoder does better than transfer learning. This is testament to the benefits of actually being able to train on data from the same domain, as opposed to doing cross-domain training. As a result of this, one of the questions that has kind of arisen in the community is how can we exploit what I would call data sets of opportunity? This is different sources of real RF data that have micro-Doppler signatures in them. This might be data which is acquired from other sensors in an RF sensor network. So you might be observing the same participant doing the same human motion, but you have multiple sensors. So you have data that is potentially at different frequencies, different bandwidths, observing the subject from different angles. But you might also have access to data from colleagues or other sources where similar experiments have been conducted elsewhere. So you might have the same activity classes, but perhaps in this case, you're dealing with sensing data that's acquired from a different sensor that has a different frequency, a different bandwidth, potentially observing the test subject at a different angle. And of course, there's different participants which are involved. In the most general case of this problem, you might consider the case of trying to pre-train on data from RF data sets that even potentially have different classes, in addition to all the different variations that I've cited above, so differences in frequency, angle, and participants. This is actually a strain of research that we've been working on since about last year, and in this particular paper, I'd like to focus on really the most elementary, perhaps, of these different sources of real RF data. And I want to focus on the challenges involved with training on data that simply has differences in frequency and bandwidth. So we're talking about differences in the transmit waveform itself. So for the purposes of the study I'd like to present to you today, we're considering data that's acquired at the same degree of observation angle. So all of the sensors are directly facing the participant and the motion is along the radar line of sight. The three sensors that we're considering is a 77 gigahertz TechSense instrument board, which has been programmed with a FMCW waveform of 750 megahertz bandwidth, a 24 gigahertz AnchorTech software-defined radio kit, which has been adjusted to have a bandwidth of 1500 megahertz, and a see-through device, which is primarily developed for respiration detection and occupancy detection, which is an ultra-wideband impulse radar that has a maximum frequency of 10 gigahertz and nominally a bandwidth of about 4 gigahertz. The data that we've acquired for 6 classes is shown on the slides here below. MTI is applied to kind of eliminate some of the noise and clutter in the data. But you can see that essentially for the same activities, there are a lot of commonalities between the signatures that are acquired from each of the sensors, but there's also differences. The primary difference is that there's going to be a different scaling in the Doppler domain so that you see a larger amount of Doppler shift in the 77 gigahertz as opposed to the 10 gigahertz domain. But once you've done all the image processing and you've prepared these signatures for input into a deep neural net, in terms of imagery, this is the kind of images that we're going to be using and inputting into our network for seeing its performance. We actually collected a total of 11 classes, and as a first step, what we did was we wanted to take a look at transfer learning as a baseline to seeing how well we can perform. So this would be a network that you might apply if you really had such little amount of data that you really had nothing to really go on in terms of training, and so you might be interested in, therefore, pre-training on optical imagery. And so the pre-training of the network was done with ImageNet, but then afterwards we had fine-tuning done with the 77 gigahertz, 24 gigahertz, and see-through data. And then we tested on each one of these frequencies as well. So you can see that in the cases where you've done the fine-tuning on the 77 gig data and you've tested on the same frequency data, that you get the greatest performance. And so if you look on the table here, training on 77, testing on 77, you get close to 90% performance. If you're training on 24 gigahertz data and testing on 24 gigahertz data, then you get about 85, 86% performance. And similarly with the see-through data, if you're training on the 10 gig data and you're testing on the 10 gig data, then you get an accuracy of about 83%. And you know, I'm not concerned at this point with what the absolute classification accuracies are. What I'm more interested in is how these classification accuracies change if I this time take networks that have been trained at a different frequency, and now I'm using that to test at one of the other sensors. And so if you look at the cross-frequency classification results, where you've trained on one sensor, but you've tested on a different sensor, there is a huge drop in accuracy. So we're talking about, you know, over 60, 70% drop in accuracy. And so the notion that somehow, well, I have RF data, it doesn't really matter what the frequency is, it's close enough, they look similar enough, you know, shouldn't this perform better if at least I have some data at a different frequency and I use that for training? Well, the differences in phenomenology are significant enough that it really hurts you to do this kind of a cross-frequency training. Alternatively, we can take a look at using the convolutional autoencoder, which doesn't have any pre-training on data from a different domain. So in this case, we would be pre-training on data from one sensor, fine-tuning potentially on data from a different sensor, and then yet again testing on data from a different sensor. In this case, we're concerned with a couple of different scenarios. So if we look at the tables that I have on this chart here, I want you to initially look at the testing accuracy for the cases which have been highlighted with a red box. These are the cases where the pre-training sensor, fine-tuning sensor, and testing sensor are all the same. And in that case, you get the best possible performance, over 90% performance, 91, 92% performance on this data set with 11 classes. When you start having differences in frequency, you can see that the performance starts to drop. So the first thing that you can do is pre-train on one sensor, but fine-tune on the sensor that is the same as in your test data set. And in that case, you can see that you have a performance drop where instead of getting over 90%, you're getting accuracies which are now in around like 75, 80, 81, 83%. So just fine tuning on the same frequency data doesn't really save the day. The fact that you've pre-trained on data that was at a different frequency is still causing you to have a significant amount of performance loss. In this case, about 10% performance drop. Of course, the worst possible scenario that you could have is when you're pre-training and fine-tuning on a different sensor and then testing on yet a different sensor altogether, in which case your performance is really hitting the ground. And so you get quite a low amount of performance. So you next might wonder, well, what can I do to try to increase the performance that I've had? Since we're considering cases where there's a small amount of training data available, we are limited in terms of our total number of samples. And so one train of thought that you might have is, well, let me think of ways that I can increase the total amount of training data I have. If I just hit the network with more data, then it'll be able to better generalize to data of other frequencies, and therefore we'll be able to get a boost in performance. So along those lines, what we did was we investigated how we could use generative adversarial networks for the purposes of data synthesis. And so there are a lot of different GANs out there, but the type of GAN that we looked at specifically in this work is the auxiliary classifier generative adversarial network. It consists of a generator and a discriminator, but additionally it also takes in the class labels so that it outputs to you the different classification results. And on the bottom left corner of the slide, you can see some samples of generated spectrograms, which we've shown for a particular class. And so you can see that they do bear good resemblance to the measured data, at least in terms of visual comparison. The specific details of the AC-GAN architecture that we implemented are shown here on this slide for your reference. But one of the important problems that we encountered when applying generative adversarial networks to the problem of micro-Doppler synthesis is the issue that a lot of the samples are actually kinematically inaccurate. And this chart is actually taken from a recent publication that we made on analyzing the kinematic fidelity of GAN synthesized signatures. And what we've shown here is that there are a lot of different artifacts in the data which in fact result in degradations in classification performance. So examples of some of the imperfections include cases where the target signature has kind of leaked into sensor or noise artifacts in the data. Other examples could be disjoint micro-Doppler components, which are completely disconnected from the main Doppler signature, and hence would not ever happen in real life because the human body is a connected object, so you wouldn't have cases of disconnected micro-Doppler in that fashion. Other examples would be cases where you have kind of symmetric positive and negative frequencies. So if we look at the falling signature on the left, where we've highlighted the negative frequencies, you know, in the case of falling, you have falling in a particular direction. It's an impulsive activity. You're not going to really have positive or negative frequencies in that case. And so just the existence of these negative frequencies themselves is causing there to be a deviation from what would be the typical target signature, as we know from physics. And in some cases, we might have classes which are actually generated that might map to other classes. So we might be trying to simulate falling, but we have this addition of a bump here in the far right-hand column, as you can see. And that bump would actually correspond to what might be actually termed a progressive fall. Instead of directly falling from a standing state into a lying down state, we might have initially fallen to our knees and then fall into the ground. So hence the appearance of two kind of impulsive bumps in the signature as opposed to just one. Other instances of kind of data that might map to a different class is in the bottom when we can look at the walking signatures. When the micro-Doppler is flipped, that would actually correspond to the participant walking in the opposite direction. Or if you had periods of blank spots in your signature, that would actually correspond to somebody who was walking, stopping, and then walking again. So all of these kinds of imperfections result in actually the synthetic training data misleading the classifier. And that results in degradation in the classification performance. And we've shown in previous work that as much as 10% degradation can be experienced due to this effect. So what we have proposed in the previous work was to use an algorithm for kinematic sifting, which is based on PCA. And the concept behind this is relatively elementary. What we do is we use the real training data to try to understand kind of spatially the feature space which is being occupied by each of the class. And we do a complex haul, basically around all of the signatures that have been acquired through the radar data. And we apply a certain tolerance spatially on this convex hull, and we basically use this as a way of sifting through the synthetic data. And we say that, you know, if the synthetic sample falls outside of a certain tolerance of the convex hull, then we're going to reject that synthetic data as being not accurate in terms of the target signature. And we're going to keep it if it falls within the convex hull. And so by applying this reasoning from an initial set of 10,000 signatures generated by the AC GAN, we rejected 4,000 of those signatures and kept 6,000 signatures for the purposes of pre-training. So what we're showing on this slide here is the results that we get from pre-training a convolutional autoencoder on synthetic GAN-generated 77 gigahertz data, fine-tuning on either real 77 gig, real 24 gig, or real 10 gig data, and then testing on each one of those sensors themselves. And if you look at this, you can see that we do perform better than pre-training on optical imagery, but we do perform a little bit worse than what we would get from a conventional convolutional autoencoder, which is only using real data. This is somewhat expected because, as I said, the GAN data is not 100% kinematically accurate. There are imperfections, and that would reduce the overall testing accuracy. But what's more interesting to note here is that even when you've hit the network with a large amount of training data, so instead of just having, let's say, 100 or 200 samples, we now have 6,000 samples that we're using for training, we still have losses that are incurred when we do cross-frequency types of calculations. So if you look at the case where we've pre-trained on 77 gig, fine-tuned on 24 gig, and tested on 24 gig data, we still have a testing accuracy of 77%, which, albeit is not 10 or 15% worse. That was what we were seeing in previous results when we applied the convolutional autoencoder. We were seeing as much as 15% degradation when we were doing the cross-frequency, some of the cross-frequency cases, but we still have you know, about 7-8% performance difference between what we would get if the data of if the frequencies of all of the data was consistent. And so what this tells us is that really this problem cannot be solved by just hitting the network with more data or trying to generate synthetic data. The differences in the phenomenology that are occurred between the transmit frequency and bandwidth differences is a significant difference. We can't just say, oh, this is micro-Doppler data from RF sensors, it's close enough. No, it's really not close enough. There are significant differences that require us to kind of uniquely deal with this problem using generative adversarial networks. Using GANs reduces the cross-frequency training loss, but it doesn't entirely close the gap. Even with fine-tuning, we can see cross-frequency training losses at about 7% when we're using the GANs. And of course, if we have a small amount of data, then these losses become even larger, as much as 15%. So in our future work, what we plan to do is investigate novel GAN architectures for the purposes of domain adaptation and style transfer. And the key aspect here is not to just take some of the networks that have been already published in the computer vision literature for this purpose, but to really think about how we could do this in a way where we incorporate our knowledge of kinematics and physics and the models of how the human body actually moves so that we can encourage the GANs to generate signatures that have high kinematic fidelity. Along this line, we've actually just published some initial work, which is coming out this week in the International Radar Conference, that includes the design of a multi-branch discriminator with embedded kinematics. If you are interested in this work, I would be glad to send you the paper that we have there, which explains how we've actually improved the matching of the target domain in the synthetic data with that in the real data. And I would be glad if anyone wants to have any questions or to reach out to me in this topic. In general, my email address is posted here. It's scgurbuz@ua.edu. And I've also included a link to my lab website here if you would like to kind of follow our work in this area in general. I'd be very interested in talking and having discussions with anyone who's interested in this problem of multi-sensor exploitation, cross-frequency training, and radar sensor networks. The project that we have currently is supported by the National Science Foundation Cyber Physical Systems Program. And so I would just like to conclude by thanking NSF for their support, and as well as you, the listeners, for listening to my talk. I appreciate your time, and I hope that you have a good conference. Take care.